As the last part of our structural analysis unit here, where we've been looking at trusses, we're going to look at something a little different called frames and machines. So frames are kind of similar to trusses. They're generally bodies that have, multiple members on them, but the major difference is that they're often indeterminate. So like here, this looks kind of like a truss, but I have two pinned end members, right? So this is pinned here and this is pinned here. And so I would have these forces, reaction forces, that I wouldn't be able to figure out with my 3 equilibrium equation. And then we also have machine. So maybe this is like a pair of pliers or something. Here's a pair of pliers. It moves in and out like this, right? Holding onto something here. This would be a machine. So a frame supports load and is stationary, so it's similar to a truss. So a frame just supports the load, while a machine transmits those forces. So it contains moving parts that transmit those forces. That's the major difference between a frame and a machine. But each of these systems are indeterminate with just our equilibrium equation. So what we're going to have to do with frames and machines is break them down into individual parts. So what that looks like is, let's say I've got some frame like I drew at the beginning here. This member, say I've got, here's member A, B, C, and I have 2 pinned ends, right? So my reaction forces, I have a CX, a CY, an AY, and an AX. And let's say there was, some kind of loading on it. Maybe there was some force put onto the member itself. A force and a moment. Something loaded onto the members so that they won't be 2 force members. Remember, 2 force members have pinned ends, but they have no load on the member themselves. So here, these aren't 2 force members, so what I want to do is I want to break this up into individual components. And we usually do this at the connection points. So for this example, I would break it up at B, for example. Right, so I can have AY, AX, BY, and BX. If I break it up like this, and I had that moment applied here, and I can analyze both parts, every piece of the frame separately. So this would be one broken out piece, and then if I break it up on the B side, where I have that CY and CX that I drew, now when I draw this BY and BX, my magnitudes are going to be equal and opposite. Right, so now my BX is pointing towards this, and instead of BY pointing down, it's pointing upwards. So my magnitude and direction, my magnitudes are going to be the same, but where I've broken it, their directions are going to be opposite. And we have this concept similarly in trusses, but here's going to be very important that we keep these the same, because oftentimes we'll be solving, say, one side of this frame, and we're going to need these results for BX, BY, so that we can solve the other side of this frame to get these reactions and have something that is determinate. So our process for looking at these is going to be to isolate every part of the frame. Right, so we're going to isolate each part and draw a free body diagram for each. So that'll be our first step. Our second step will be identify any 2 force members if we do see them. So identifying 2 force members can really help simplify down things. And then finally, once we have everything broken out, we should be able to go ahead and apply our equilibrium equations. right? Sum of our moments, sum of our forces equals 0. So those are our basic steps. Really the most important one being break them out, isolate each part, usually at a pinned connection. At each connection, isolate each part, and see which part you can solve for, and then you kind of backtrack your way down. Let's take a look at some examples. In this example, I want to find the vertical and horizontal components of the reactions at C. And I can see if I were to draw the standard free body diagram for this, as we've been doing, I would end up with my C reactions here, Cx and Cy, but at A there's also a pin, right? So I would have Ax and Ay, and this would be an indeterminate form, right? I only got 3 equilibrium equations, but 4 unknowns. So what I'll need to do is split this guy where I best see fit so that I can try to solve for those reactions at C. So if I split this guy into 2 free body diagrams, I have from A to B, I've got this Bx and By, Ax and Ay, and then between B and C, I have Cx, Cy, By, and Bx. So here it's like, if I split them into both parts, I'm still looking at 2 indeterminate forms, right? But one thing we said was really critical is be sure you can identify a 2-force member, right? Something with 2 pinned ends and no load applied. So AB here is actually a 2-force member. So what we can do is, instead of having this free body diagram with this Bx and By, I'm actually going to call it just the force through member AB. Just the force through member AB. So F, AB. So now if I look at just this guy, just this portion of the frame that we found, it has everything that I'm looking for in trying to be able to solve a problem, right? I want to find Cx and Cy, so those are in my diagram. And I only have 3 unknowns now. I have FAB, Cx, and Cy. So I can go ahead and apply my equilibrium equations here to find what that Cx and Cy is. Make a little room here. Set up my equilibrium equations based off of this free body diagram, this portion of my frame. So what I'll do is I'll go ahead and take a moment. And even though I'm solving for C, I'm going to take a moment about C so that I can find FAB. Since it has an X and Y component, it's going to come up in my X and Y equilibrium equations. So I'm going to go ahead and find what FAB is first. So FAB, if I take a moment about point C, I'm going to have that 2,000 Newton applied force times its distance away, it's 2 meters, minus the Y component of FAB, and I have this 60-degree angle here. So the Y component of FAB is going to be FAB sine 60 times its distance away of 4. So I get that my FAB value is 1155 newtons. And my signs did come out correctly, so it is pointing this way in the negative X and negative Y direction. So even though they didn't ask for this as an answer, I don't need to box it in as an answer. I do need it for my other 2 equilibrium equations. Sum of forces in the X direction equals 0 is going to be that X component of FAB, so negative FAB cosine 60 for the X component of that. And then my CX, I can already see I've drawn in the wrong way. I drew it in the negative X direction. But it turns out that Cx, when I do the math here, is going to be 577 newtons in the positive x direction. And my Fy be the Cy minus 2000 minus the y component of FAB. So FAB sine 60. So I will get that my Cy is 3000 newtons, and that I did draw that one correctly, that is upwards. So those are what the question asked for, right? The horizontal and vertical components of the reaction at C. So this can be really helpful when we have indeterminate systems that are indeterminate just by looking at them, and we need to break them apart. So we could have solved this system knowing what we already know about two force members and everything, but what if we have a system that we wouldn't know how to solve? Something that we might call a compound beam, where we have multiple beams together but we can't solve them. Let's take a look at an example like that. So in this example, we want to determine all the components of reaction at all supports, but we have something a little different than we've seen before, right? At point B, we have this pin through the middle of our beam. So even though it looks like a straight beam, we've got a pin in the middle of it, and we call this a compound beam. So at that pin at B, it again allows for that rotation and has a X and Y support reactions within that pin itself. So when I draw the full free body diagram for this thing, I have that fixed support at A. So I have AX, AY, and a moment at A. I have that one reaction force from the roller at C in the Y direction, and so I can already see that this is an indeterminate system, right? I've got 4 unknowns here. And as a whole diagram, I don't put in my reactions at B, but when I split this up into 2 different portions, 2 different parts of this frame, I'm going to have my internal B forces at that internal pin B, they're going to show up. So if I do my 2 free body diagrams, right, splitting it at B, I again still have those same A reactions, AY, AX, and a moment about A. I have that 10 kilonewton force, and then I have this BY and BX. And so for the C portion, again, equal and opposite. So now my BX points to the right from the way I assumed it, BY points down from the way I assumed it, and CY points up. And then there's that distributed load, which I can simplify down to be the 4 kilonewtons per meter times the 2 meters is 8 kilonewtons acting 1 meter in to the center, right? This 10 kilonewtons has a 3, 4, 5 triangle. So I can put that in there as well, where this is 2 meters and 2 meters. So these are my 2 separate, distinct free body diagrams. And when I look at these 2 portions of this beam, I can see that, oh, well, if I look at my right-hand one, my BC, it's got 3 unknowns, right? It's got the BX, BY, and CY. So that one I can solve. I can solve that as just a portion of the frame, applying all of my equilibrium equations. So if I, for example, take a moment about B equals 0, I take that moment about B, I'll get negative 8 kilonewtons times 1 plus CY times 2. So I can find that my CY reaction is 4 kilonewtons, and that I assume the correct direction. So that takes care of one of my reaction forces, and I can go ahead and solve for BY and BX here. so that I can apply them into this other free body diagram to solve for AY, AX, and this moment about A. So if I finish out my equilibrium equations from the free body diagram of BC, sum of my x forces equals 0, and of course the only x force I have here is bx, so that tells me that bx is just equal to 0. And then sum of my y forces is 0, -8, plus the value of cy, plus cy is 4. And then I drew by as a minus, but it's actually not. So what I'm going to get is that by, for this diagram, by is actually 4 kilonewtons acting in the positive direction. So what I want to do is I want to fix this free body diagram on the left side before I transfer all these values in. So let me redraw this so that everything is drawn in the correct orientation. So since I got that by was actually a positive value over here, right, by, oops, this is what I got for by. It means that it'll be equal and opposite. So by is going to be pointing down over here, and then bx is also equal and opposite, but bx is just 0. So I'm not even going to put it into this left-hand side AB free body diagram. I'm just going to say that this by that I got is 4 kilonewtons and it's acting downwards. So now I should be able to use my equilibrium equations to solve for AX, MA, and AY, because I have just those 3 unknowns. I was able to take information from my BC portion, pop it into my AB portion so I could finish solving. Right, so I'll take a moment, let's take a moment about point A. Again, it's up to you whichever one of these equilibrium equations you want to do first. I usually start with a moment because I find that it eliminates the most one of my unknowns. And so if I take a moment about A, what I'm going to have is negative MA minus the y component of that 10 kilonewtons, so 10 times 4/5 times its distance away, which was 2 meters, minus by, which we said was 4. I'm just going to put in the 4. 4 times its distance away is 4. So, interestingly enough, I actually get that my MA here is 0. So there is no moment component at the fixed reaction. So MA equals 0. I'll go ahead and do my other 2 equilibrium equations. So sum of forces in the y direction equals 0. I will get AY minus the y component of that 10 kilonewton force minus by. So AY is going to be 12 kilonewtons. And I assume the right direction, 12 kilonewtons upwards. And then I can see if I do my sum of forces in the x direction, again, it's going to be just like this bx guy over here. I'm going to get AX. Oh no, there's an x component. Oh, sorry. There's an x component to my 10 kilonewtons. So AX minus 3/5 times 10. So I do actually have an AX component here. AX is 6 kilonewtons. And that's it. Those are my reaction forces. The moment about A is 0, AX is 6, AY is 12, CY is 4 kilonewtons. Right, all of them were in kilonewtons. I don't actually need to list those internal ones at B. They were more like a stop-along point to unite the 2 halves together. Let's take a look at another type of example. So this example is a little bit more complicated than the past examples we've seen. So we have a man who is holding down this rope attached to a pulley, and this rope is not being pulled through the pulley, but is actually at the center of the pulley there, holding onto the pulley itself. And then there is a rope wrapped around the pulley from F to E to D to C, all the way down to the beam at B. So he's standing on the beam, pulling down on this pulley system, attempting to lift up the beam at point B. So we want to know if this 75 kilogram man can lift this 40 kilogram B off the roller at B. We want to know the tension in the cable at the moment that he's lifting it off of this roller. So the second that that beam comes off in the slightest amount, that's what we're trying to figure out. That's what we're trying to figure out, what the tension in that cable is going to be at that time. So that's a really critical piece of information there, that at the time that it's lifting off of the roller at B, because what that tells us is that this reaction at B here that is being experienced at that moment in time is going to be 0. So this By at the roller here is going to be 0 at the moment that the beam is starting to lift off. Second, it's starting to lift off from the force of him pulling it down to pull it up through this pulley system. So we have this By equals 0, and then we can set up a whole slew of free body diagrams at different points to break up this system, right? So we could draw one for the beam itself, right? So if I draw the beam itself, I have those reactions at A, AY, and AX from the pin at A. We already said that roller at B, there's no reaction there, right? It's being lifted up off of that roller, so there is no support from the roller at B. But there is that tension force. There is that tension force from being pulled up through that rope there. And then they also gave us a weight for the beam. So this is one of the rare cases. We don't see this often in our example problems, but we do have a weight. The weight of this beam was given to us, call it weight beam, as 40 kilograms. I'm going to multiply that by my 9.8 to get an actual force here, right? A newtons. My weight of this beam is going to be 40 times 9.8 in newtons. And then, of course, there's one more force on here, and that is the normal force from the man. And we're going to have to figure out what exactly that normal force is, right? So here we have 4 unknowns, so we're going to have to continue on with these free body diagrams. So let's make a free body diagram of the man himself, and maybe we can find what that normal force is. Oops. Nope, not that. So my man here, he is experiencing the normal force from that beam, right? So that's what we want to find. We want to find what that normal force is. And we know that he himself has a weight. He has a weight that was given to us in the problem. 75 kilograms was his mass. And so to get his weight, we could just multiply by that 9.8, just like we did for the beam. So his weight is that 75 times 9.8. But then also, he's holding on to this rope up here, right? This rope from E to H. He's holding on to this rope, and that's another force that is acting on him. He's acting on the rope is acting on him, so I'm going to call this T2, right? This tension in this rope here, this rope is not connected to this other longer beige rope. I'll make this the red rope here. This red rope and the other rope are not the same ropes. They are 2 different ropes. If we look at this pulley in detail, if I were to do a free body diagram of the pulley itself, I would see the tension T2 that's being connected to the man, and then the tension from the rope that's going around the pulley, which is the rope that goes from F to E to D to C to B. So that is all the same tension, but it is not the same tension as the one going to the man. So we can see we still kind of have too many unknowns here, right? I can go ahead and start setting up some equations and see if I can backtrack my way to get some things to work out. So like in my free body diagram for my man, if I wanted to set up that free body, or if I wanted to set up that equilibrium equation, sum of forces in the y direction, since I only have y directional forces here, y equals 0, I'm going to get T2 minus the weight of the man, called the WM, weight of the man, plus N. Right, so the only thing I know here is WM. I don't know the normal force and I don't know T2. But if I look at this pulley diagram that I drew over here, I can again give myself an equilibrium equation. If y equals 0, I'm going to get two t's, right? T plus T minus T2. So I can say T2 equals 2T. And with this information, I can substitute this guy back into this equation over here for T2. And then if I take this again, I will have a normal force equation in terms of T. Then I should have just 3 variables back in my original free body diagram for just the beam. Right? So if I substitute in this 2T, I'm going to get my normal force equals, this WM term when I multiply it out is 735. 735.8 minus 2T. Right, just substituting a number in for WM and substituting in 2T in for T2. Gives me this equation here. So I can take this equation and substitute it in to my free body diagram here. So now I have just 3 unknowns, right? I have AX, AY, and T, which now my T appears in 2 places, right? It'll appear here, N equals 735.8 minus 2T. So that when I set up my equilibrium equations for this beam, I'll have this equation included in those equilibrium equations. I'm going to move these other free body diagrams that I was really kind of using temporarily, right? They were intermediary steps to fully define, I guess, this beam in terms of just 3 unknowns. So I'm going to go ahead and, looking at this beam, my question only asked me to determine the tension in the cable attached at B. So I'm only interested in my T terms here. So if I look at this beam and take a moment about A, I don't actually care about what those reactions at A are, so taking a moment about A would be perfect, so that I'm not actually needing to solve for those. I'm just looking for the T terms. Right, so my moment about A is 0, so that's going to be my N, right? So negative N, negative, that N equation that we found, 735.8 minus 2T, times its distance away. That normal force from over here is 0.8 meters. 0.8. And then just walking on down the line, next I have WB, so minus that 40 times 9.8 was 932.4. And that weight of the beam acts in the center of the beam, right? And this beam is 3 meters long. So it acts halfway through the beam, so multiplied by 1.5 distance from A. Okay, so that's WB times the distance from A. And then the last thing I have is that regular t at the end down here. So plus t times its distance away of the full 3 meters. So now all I have are t's in this equation. So I do the algebra, right? Punch that into my calculator. And I get that t is about 512 newtons. And that's it. So with these frames and machines systems, it's really about breaking them up into pieces and seeing which pieces you can solve or get into other equations that you can substitute back into other pieces and parts of these frames and machines.